Now, who can tell me about the energy challenges of the early 21st century? The teacher's question echoed through the spacious classroom, filled with students eager to showcase their knowledge. The year was 2125. Holographic projections flickered to life, showcasing a bygone era when humanity grappled with an energy crisis. The students, beneficiaries of a century of progress driven by quantum computing, prepared to delve into the challenges their ancestors had overcome. The world of 2025 was heavily reliant on fossil fuels. Coal, oil, and natural gas powered industries and transportation. But these resources were finite, and their extraction came at a heavy environmental cost. Greenhouse gas emissions were altering the planet's climate. Renewable energy sources like solar and wind offered a cleaner alternative. However, their dependence on weather conditions and limitations in storage technology posed significant challenges. Nuclear power, while capable of generating substantial energy, carried the risk of accidents and the challenge of radioactive waste disposal. Energy storage and transmission in 2025 were also inefficient. Batteries had limited capacity and power grids suffered from transmission losses. The world desperately needed a revolution in energy production, storage, and distribution. Enter quantum computing, a revolutionary technology that emerged in the 21st century. Unlike classical computers that relied on bits, quantum computers harnessed the power of qubits. Qubits could exist in multiple states simultaneously, enabling computations at speeds unimaginable before. This breakthrough unlocked solutions to previously insurmountable problems, including those in the energy sector. Quantum computers could analyze complex molecular interactions. This capability proved critical in developing new materials and optimizing existing processes. The development of room temperature superconductors, for example, drastically reduced energy loss during transmission. Fusion, the process that powers the sun, had long been considered the holy grail of energy production. It promised clean, abundant energy from readily available sources like seawater. However, achieving and sustaining the extreme temperatures and pressures required for fusion had been a monumental challenge. Quantum computing changed the game. By simulating and manipulating the behavior of plasma at the quantum level, scientists were finally able to design and build viable fusion reactors. These reactors, unlike their fission counterparts, produced no long-lived radioactive waste, paving the way for a truly sustainable energy source. Quantum computing also breathed new life into existing renewable energy sources. New materials designed with the help of quantum simulations dramatically increased the efficiency of solar panels. They could capture a wider spectrum of sunlight, even in low-light conditions. Similarly, wind turbines benefited from quantum optimization. Their design and placement were refined to maximize energy capture from wind patterns analyzed with unprecedented accuracy. These advancements made solar and wind energy more reliable and efficient, further reducing reliance on fossil fuels. Section 6. Quantum batteries storing the future. The development of quantum batteries addressed the critical issue of energy storage. These batteries, utilizing the principles of quantum superposition and entanglement, possessed significantly higher energy densities and faster charging times compared to their 2025 counterparts. Imagine a world where electric vehicles could be fully charged in minutes, or homes could store days, even weeks of solar energy. Quantum batteries made this a reality. Section 7. The power of invisibility. Wireless quantum energy transmission. Perhaps the most awe-inspiring development was wireless quantum energy transmission. Based on the principles of quantum entanglement, this technology enabled the transfer of energy over long distances without the need for physical wires or loss due to resistance. Imagine a world where energy flowed like information, beamed wirelessly to power homes, vehicles, and even entire cities. Section 8, A Century of Progress. 2025 versus 2125 energy efficiency. The energy landscape of 2125 stood in stark contrast to the challenges of 2025. Fossil fuels were relics of the past, replaced by clean, efficient, and nearly limitless energy sources. Cities, once choked with smog, now boasted clean air and a tapestry of green spaces. Energy consumption overall became significantly more efficient. Homes and buildings designed with advanced materials required a fraction of the energy they once did. Transportation systems, powered by fusion, electricity, and wireless energy transfer, were both fast and environmentally friendly. Section 9. Beyond the Horizon, Exploring the Unexplored. The journey of scientific discovery, however, is never truly over. As the students of 2125 learned about their past, they also looked to the future. Research on even more exotic energy sources like zero-point energy, dark energy, and even artificial black hole reactors were already underway. The possibilities, much like the universe itself, seem boundless. The legacy of quantum computing in revolutionizing energy production was just the beginning of a new chapter in human ingenuity and the quest for a sustainable future.